Greetings and welcome to the Dr. J vlog series. It is Thursday, June 19th, 2025, and on Thursdays we talk about knowledge and science. So yeah, this week we've been talking about the sun and all of the different vlogs from all the different perspectives. And so today we're going to be looking at it in terms of knowledge and science. And so of course the sun itself is an endlessly fascinating object about which I shared a number of fun facts, or what I called sun facts, in Monday's vlog. Of course, the core is extremely hot. I talked about that, as in 15 million degrees Celsius, 27 million degrees Fahrenheit. But really, who's counting when you get up to that high, right? It's just incredibly hot. But I hear it's kind of a dry heat. Anyway, and then the sun cools as you get closer to the solar surface. And then ultimately, as you get to the photosphere, which is what we see. It's only about 5,500 degrees Celsius, or about 10,000 degrees Fahrenheit at that point. So that's, again, what we call the sun's surface. But then as we arrive at the sun's corona, or outermost edge, the temperature again becomes incredibly hot. In fact, as much as 2 million degrees Celsius, or 3.5 million degrees Fahrenheit. And here's the thing, we don't know exactly why that's the case. So it's the conundrum known as the coronal heating problem, which astronomers have been working on since middle part of the 19th century. Specifically, during the 1869 total solar eclipse, scientists were able to observe the incredibly faint corona of the sun. And their observations revealed a feature in the corona that they thought, at least at that time, was a new element that they named appropriately coronium. Now, with better theories and observations, we learned 6 decades later that that so-called new element was actually simply iron, but of course heated to temperatures much higher than the sun's surface. So, dating back to that initial 1869 measurement, we had the first evidence then of the corona's extremely warm temperature. And so how come the plasma there reaches such a high temperature? And where's the energy coming from to produce such a high temperature? So this is an important problem so that we can understand the sun better, obviously in the first place, but especially so we can perhaps understand and predict space weather better and protect humans. And plus, the knowledge can also help us understand other stars and perhaps other phenomena in the universe as well. It's the great thing about science, constantly learning, increasing our store of knowledge, hopefully our understanding. All right, so again, there are currently 2 main hypotheses intended to explain how the energy from the sun ends up heating the corona. So the motion of waves, and then an explosive phenomenon known as nanoflares. All right, so the first theory is based on our understanding of the sun's surface as a kind of roiling and bubbling entity, a lot like a pot of water. That's the analogy that's often used. And as the plasma convects, that is, as the hotter material rises and the cooler material sinks down, it generates the sun's huge magnetic field. The magnetic field can move and wiggle in a specific kind of wave, known as Alfvén waves. And this is a type of wave that propagates through a plasma. A plasma is essentially just an ionized gas in the presence of a magnetic field. And so they're characterized by the oscillation of ions along magnetic field lines, driven by the tension of these field lines. In effect, the protons and the electrons above the sun's surface are being pushed around violently. And astronomers think that the charged particles help to stir up this phenomenon that might carry the energy then to the corona, heating it up again to these incredibly shocking temperatures. Okay, theory number 2, the other possible explanation, involves something known as nanoflares. So as the sun's plasma tumbles and circulates in the upper layers, it twists the star's magnetic field lines into these knotted, messy shapes. And once the lines can't take the stress anymore, kind of like a rubber band, they're hypothesized to snap in an explosive event called magnetic reconnection. And this sends charged particles flying around, heats them up, and this phenomenon is what's known as the nanoflare. The nanoflares then are allegedly carry the energy then to the corona. And astronomers have actually observed a few examples of the nanoflares with modern space telescopes and satellites and so on, and one other development, which I'll talk about in a moment. So the question is, well, what explains this? Well, as with most things in nature, it's probably not just the sun simply, launching Alvin waves or creating nanoflares. It's probably more likely doing a bit of both, but we just don't know how often and precisely how these events happen as such. Well, until a little bit more recently. So then in 2018, we launched something called the Parker Solar Probe. And that's come closer to the sun than any other man-made object as of 2021. And it also provided the first close-up look at the movement of the particles that might be responsible for these extreme temperatures. And so the probe has provided evidence that these small-scale jetting in the sun's corona, driven by magnetic reconnection, ends up being responsible, or appears to be responsible for heating and accelerating the solar wind. And so we're a little bit closer then to understanding this particular mystery. And speaking of the Parker Solar Probe, it is quite the world record setter, shall we say. It's actually kind of beyond this world now, obviously. But in 2024, it reached a top speed of about 430,000 miles per hour, or almost 700,000 kilometers per hour. And that's the fastest any object we know that we've made has ever flown. And it also flew within less than 4 million miles from the from the sun's surface. And by the way, at that particular speed, you could actually travel from New York to Tokyo in the proverbial New York minute. In fact, you could actually travel from New York to Tokyo in less than a minute at that particular speed. Another thing that we learned from the Parker Solar Probe is that it turns out that the sun's corona is wrinkly. The surface of the corona isn't shaped like a smooth ball as such, but rather contains spikes and valleys that sort of wrinkle the surface. And these turned out to be coronal streamers, giant plumes of solar material rising through the sun's atmosphere. And the results, NASA said, are reshaping what we know about the sun's atmosphere and how it transforms the solar winds. One other finding I found fascinating. There are many more energetic particles that are flying off the sun than we realized. Now, particles are flung off the surface of the sun at these incredibly high speeds, and only some of them, however, arrive to the Earth. But the Parker probe's instruments have determined that they're far more numerous than previously imagined, and that they also come in different types, and that they often take very circuitous routes as they're captured by the flipping magnetic fields. And finally, I mentioned this phenomenon of space weather. Yes, that's a thing. The activities on the sun emit radiation and the high-energy particles I've been speaking of into the space environment. This, of course, then affects the conditions of the sun, the solar winds that are produced, and ultimately the Earth system as well. So this is what we mean by space weather. It refers to these conditions and their influence on the Earth, and especially the technologies that are so vital to our existence these days. So in particular, solar flares and something called coronal mass ejections, CMEs, can accelerate the solar winds, creating radiation in the form of energetic particles. Now, the average CME dumps about 1,500 gigawatts of electricity into the Earth's atmosphere, which is roughly double the power generating capacity of the entire United States. Fortunately, the Earth's magnetic field, or magnetosphere, protects us from the most harmful effects of the space weather. But, of course, some energy does get transferred into the magnetosphere, which can induce these geomagnetic storms. And that's great if you want to see some really colorful lights, if you really want to see a cool aurora borealis or aurora australis, that is the northern lights and the southern lights, respectively. Cool. But, however, these can also directly affect our technological infrastructure, affecting the strength of the Earth's magnetic fields. And these changes then can induce corrosive electrical currents, through the gas and oil pipelines, as well as surges in transformers and power lines, among other things. In addition, solar flares and CMEs can affect the Earth's own ionosphere, which is effectively a vital relay station that's bouncing radio waves to assist with communications around the globe. Okay, so the geomagnetic storms can disturb the ionosphere and can completely, for example, wipe out high-frequency radio communications around the Earth's poles for several days. This is especially bad news for aircraft that are flying over the poles in terms of disrupting their navigation systems, communications, and electrical systems as well on the aircraft. And the disturbances in the ionosphere can disrupt our communications with satellites. That's the thing that we've most heard about probably, including everything from our GPS satellites to our everyday banking needs, our computer networks, and so much more. So these are more good reasons then for investing in things like the Parker Solar Probe and additional research to understand the dynamic nature of the sun. Yes, the sun's the ultimate source of our energy in the forms of heat and light and so on, but it's the ultimate source of just about everything that governs our lives, no matter how technologically advanced we become. So, as much as I love the songs and the dances and the literature and the artistic renderings of the sun and so much more, I equally value the science of the sun. Our lives quite literally depend upon such knowledge in more ways than perhaps most of us even realize. All right, that's it for today. Thanks for listening. And as ever, may you and yours continue to create peace in your lives, nurture love in your hearts, and dole out hugs in abundance. And I hope to see you tomorrow as well. Take care.